so we're going to have a quick look at some of the a tiny bit of AS things that you learnt in AS, and then a significant chunk of stuff that you learnt in A2 to do with inferential testing. I know it's probably the bit that maybe you're put off from the most, but hopefully going through this video will make you realise quite how little there is, and also how, I know it probably doesn't feel that way, but how simplistic it is. So please don't be put off. You've got your C in your maths, GCSE or above, so you'll be more than capable of this really kind of these simple concepts. A lot of it, if you get really stuck, is just memorising phrases, learning things off by heart. Okay. So the first one was the sign test, which is what you was introduced to with Andy. So of course you'd use the flow chart, you'd use the reasons why to identify why you're going to conduct the sign test, and we'll have a look at that in a moment. The first thing that you would do is subtract condition 2 from condition 1. Okay, so 15 take 12 is 3, 16 take 12 is 4, and 14 take 16 is minus 2. The next thing you would do, for every number, you would look in this column here, and every number that was a plus, you would put a plus, and for every number that was positive, you would put a plus or a positive symbol in there. So you've got 3, which is positive, because 15 minus 12 leaves 3 positive numbers. So you'd put a positive in that one. 4, it's a positive number, so you'd put a positive in that one. And 2 is a negative, so you'd put a negative number in that column. Okay. Then you would identify the least frequent sign. Well, the least frequent sign was a minus number, was minuses. And then what you would do is you'd count up the number of least frequent flat signs, and that is your calculated value. So in this one there is 1 minus, so the calculated value is 1. Okay, as simple as that. So please don't overthink it. The next thing you need to know is, well, not the next thing, because in that process you would have gone through this, selecting the statistical test first, but sign test nice and easy from AS. So you're presented with, you've conducted some research and you've collected data, then you need to select your statistical test, or you'd probably know which statistical test you were doing. You do it in the process when you were planning your experiment. You've got your data, now you want to analyse it. So there's a couple of things you need to know, and we've been through this loads and loads of times. When to use a parametric test is the first thing you need to know. So you use a parametric test when it's interval level data, when the data is not skewed, so it's a normal distribution, so that nice even bell curve, and then when the standard deviations of a similar number between conditions. So if you've got a very large standard deviation for condition 1 like 10, and you've got a very small standard deviation of say 2 for condition 2, then you would not be able to use a parametric test. Remember, standard deviation demonstrates the spread of the data. Then the key thing, so if you were asked the question to identify whether you could use a statistical test, the 3 things you would talk about. So you've identified that you can use a parametric test if it's met the ones above, or you can't use a parametric test if it's not interval level data, the data is skewed, or the standard deviations are very different. The 3 Ds then, please remember this. You've got levels of measurement, so the data, nominal, ordinal, interval. So nominal is naming, frequency, discrete, separate categories. Ordinal, placing things in a rank. Interval is a standardized unit of measurement, so the difference between, and the intervals between each unit are the same. So the difference between 1 centimetre and 2 centimetre is the same as the difference between 5 centimetres and 6 centimetres. It's standardised and equal. Anything else where it's not equal distance between the two would be ordinal, so ranked, placed into an order. Experimental design, repeated measures, matched pairs, independent groups. Repeated measures, everyone in the sample does all conditions. Matched pairs, they're matched together on participant variables that might affect the study. So you would pick variables that you think might affect the study. For example, if you're looking at memory, IQ is a significant effect on memory. Gender, you might consider those things. So just think carefully if you're talking about matched pairs. And independent groups, all participants do one condition. Okay, remember, repeated measures and matched pairs can also be called related measures, and then independent groups is unrelated. Related because people in both conditions are related. Repeated measures is the same people, or matched pairs, they're very, very similar. Independent groups, they are very different, so they are unrelated. And finally, is it looking for a difference or a correlation? So you would talk about those as well. So whether it's a different or if it's correlation, you'd see the word relationship. Or you would talk about comparing two bits of data. Okay. And then this you're just going to have to memorise. Can you use a parametric test? So yes, it's interval, it's not skewed, standard deviations are similar. Is the data correlational? Yes, it's Pearson's R. So remember, Spearman's row and Pearson's R, or Spearman's and Pearson's, sound similar. They are both correlational. So I always remember that, because Spearman's, you've got the line of spear like the line of best fit, that's correlation. Pearson's sounds similar to Spearman's, so you could think of it like that. Pearson's, P for parametric, so you can use a parametric test for Pearson's, you can't for Spearman's. If it wasn't correlational data, you ask yourself the experimental design. If it was independent groups, it would be unrelated T. If it was matched pairs or repeated measures, so it was independent groups, then it would be related T. Remember, unrelated independent groups are two people aren't related, then they in the two conditions are similar. And then we go through the same, so you can't use a parametric test. It was interval or nominal data, the data was skewed, or the standard deviations are very different. So you ask yourself, is the data nominal? If the answer is yes, you have to decide, was the experimental design. If it was independent groups, it's chi-squared. If it was repeated measures or matched pairs, then it is the sign test. If the data wasn't nominal, you have to ask yourself, was the data, so if the data was ordinal, essentially, or interval, if you can't, but if one of the other things stops you from using a parametric test. Is the data correlational? Yes, Spearman's row, because of course we know Spearman's correlation, the spear is the line of best fit, but it's not Pearson's, which begins with a P, because you can't use a parametric test. Is the data correlational? No. Was it independent groups design? Yes, Man Whitney U. No, Will Coxon. So there you go, that's it, just going to have to memorise that one. And then the use of statistical tables and critical values in the interpretation of significance. So this is the bit where people get confused, but actually you'll be absolutely more than fine with this. So first of all, you have the calculated value, which is what the psychologist calculated. So in this case, I think previously it was the sign test, so the calculated value was 1. That's what we've worked out, that's what we've calculated. The critical value, believe it or not, can be found in the critical values table, which is for the sign test here. And then what do you need to know to identify the critical value? So we know the calculator value, we want to find out the critical value so we can compare them and decide if the results are significant. You need to know the number of participants, so let's say it was 18 for the test that we just completed, even if it wasn't. Okay, we have to know whether it's one-tailed, so a directional hypothesis, or two-tailed, so a non-directional hypothesis, as simple as that. Directional, boys will do better than girls, so-and-so will score higher than so-and-so, whatever, it gives it a direction. Two-tailed, non-directional, it could go either way, there will be a difference between blah blah blah. Okay, so we don't identify which is which. And then the significance level, and this could be asked, this is coming directly from the specification. So if the significance level, which is the standard one, which is this one here, just change the numbers depending on which one we talk about, is 0.05, this means there's a less than 5% likelihood that the difference that we've identified would occur if there was no real difference between the conditions. Or what we've been saying, this means there's a less than 5% likelihood that the difference is due to chance and not due to cause and effect. And the researchers would have a 95% confidence level. So let's say that it was 18 participants and we used a one-tailed. So we go across, it's one-tailed, 0.05 or 0.05 significance level, so we're happy to take that 5% chance that we might say it's significant when actually the results are due to chance, and then we get the number 5 here. Finally, the next thing you need to do is go down to here, so remember your calculated value is 1, your critical value is 5. For significance, the level of the less frequent sign is equal to or less than the value of the table. So the value of the less frequent sign, I would then write 1 is equal to or less than 5. So that is correct. So therefore we would confirm that our results were statistically significant, with less than a 5% likelihood that the results, even though we found them significant, are actually due to chance. So we would accept the alternative hypothesis and reject the null hypothesis. So that's it, nice and simple. Remember, when you're answering a question where it asks you to use that, you must name everything you've used. So you would say the results are significant because the value of the less frequent sign, open brackets 1, is equal to or less than the value of the table, open brackets 5. when the n equals 18, the test, we've used a one-tailed hypothesis, a one-tailed test, and a significance level of 0.05. You must mention all of those things. You'll easily get the marks. You can easily do that. And then finally, type 1 and type 2 errors. So depending on the significance level, you could make one or other of these errors, or increase the likelihood of one of those. So type 1 is the error of optimist. So O for 1, O for optimist. This is where you accept the alternative when you should have rejected it. Yes, I've definitely found something significant when that is not the case. And you could do that when you have a less stringent significance level. So it could happen at 0.05, but more like you'd increase your likelihood if P was less than or equal to 0.10. So you've increased it to a 10% level, to a 10% level. And then type 2, this is where you reject the alternative when you should have accepted it. So this is where you say, no, I've definitely not found anything, when actually you could, and that's when you have a really stringent level like 0.01, which is something that we would use for drugs because we don't want to make any mistakes. So yes, this drug is absolutely fine when that's not the case. Right, that's everything to do with inferential testing. I hope you realise it's not quite as scary because we've done it in just over 10 minutes.